Hi, in this video, we want to look at the informative value of a test and the informative value of individual questions. So remember that we're going to call it questions items throughout this. All right, so conceptually, if I have data, I want to know how informative is my data, right? So this gives me an idea of how useful it is. And should I trust it? Should I use it? Is it good enough for my application? Is it good enough for my use? All right, so in information theory, what we're going to do, we want to look at the whole test, so all the questions put together, and to evaluate, the utility of the information, and we want to look at individual items. So why would we want to do this? Well, in terms of individual items, if I'm going to go ahead and let's say I'm going to reuse those questions in the future, if it looks like those questions do not have informative value, I want to get rid of them. Also, if I'm writing questions myself, this can help give me feedback on did I write a good question or not. Also, it can give me feedback on how I can improve. The only way for me to improve is to look at where I'm weak and where I'm strongest. All right. And then, of course, if I'm going to be giving students grades, I want to know like how useful is that test in assigning grades. Now that one is definitely going to be a lesser used aspect of this, but it's still good to know. When we use data, we want to know how trustworthy, how solid are the results before we start making decisions. All right. So this example is modified from Modern Psychometrics with R. So it's in the Use Springer, Use R series of books from Springer. And here's the GitHub website for the example code. All right, so let's go ahead and let's load the data. So we're going to be using the Wilmer data set from the MPsychoR package. And we're just going to look at VPMT, this portion. This data set is used in another example in the book. And so I went ahead and just grabbed it because it's relatively easy to work with. Okay, so I'm going to build a model, and it's actually, this is an error that's not nominal. We're going to build, I should just say build a model right there. And we're going to use a race model. Now, in the example in the textbook, he actually builds a nominal response model, and some of the output that I'm about to show you is not applicable. So I didn't want to use a nominal response model. I went with a race model because that is the most well-established, most well-known model there is in item response theory. So remember, one way to get a race model, I could use the ERM package, or I could use the MIRT package. And the function within the MIRT package is the MIRT function. All right, so I tell it it's data. Here I'm saying that I just have one latent variable under the hood for this. I'm saying, so here's the model structure. I'm saying it's a race model. So remember that there's a lot of model structure assumed by the race model. And so one thing that's nice about this is that it has more assumptions required, but it requires less data, right? Remember, we always have a balance of that. If I have more assumptions, I don't need as much data to fit the model. But if I have fewer assumptions, I need more data to fit all to fit the more flexible situation. And I put it to verbose equals false because otherwise it gives information about the iterations. And for this purpose, we don't really care about that. We just want the output. Okay, so let's look at the test as a whole. Let's look at so remember, each row corresponds to a student or a subject, and then each column corresponds to a question or an item. And so if I just do plot, now something about the MERT package, when I'm using MERT package, if I don't manually go through and load, library MERT or require MERT, what will happen is I can't access those functions using the colon operator a lot of times. I can't access them using the methods techniques. So the vast majority of packages in R, if a function is called plot and I type in plot, R will look at the class, find where on my computer is a function to work with that class, and just execute it. And it's great. So this is like so I do not need to, most of the time I do not need to load the package using library or require to be able to do general methods like summary, plot, print, okay? But here in the MERP package, they didn't give that utility when they made the package because the vast majority of people actually load the packages using the library command, but I don't because I don't like package confusion. So whenever you're using a general method from the MERP package, you have to specify that's coming from that package. Otherwise, R will start throwing errors. Okay, so if I put info as my type, what it's going to do, it's going to give us an information of the informative value of the tests along our latent variable, the variable that we're trying to assess that we don't actually observe. And here, that looks very symmetric, looks very similar to a bell curve. All right. Now, if I put SE for standard error, we'll see that we have lower standard error near the center of the central tendency of what we've got going on for our latent variable. And we have greater standard error away from the central tendency. And then if I put info SE, it'll plot both of them together. And we can see that there's a, there's a relationship. As standard error goes down, the information goes up. All right, so when we see extreme values for our latent variable, that's telling us that we have less information, that we can rely on the information less for those subjects. And when the subject is close to central tendency, we have more information, it's more trustworthy results. Now I can also go with the expected score. And this plot is why I did not use the nominal response model, because here I can actually get an expected value off of here. And so you can see that the expected value increases as our latent variable increases. And we can also plot the reliability. And we see that the reliability has a similar relationship to the standard error as info does. It's just a different shape. Now we can look at item plots. So here what we're trying to do, we're trying to look at individually the informative value of each question. Now it's kind of hard to see, but they're actually shifted left and right. And there's going to be more peaked and less peaked plots on other models. Now for us, since we're doing a race model, we have parallel assumptions. We have a lot of assumptions going on. Because of that, they're actually just shifts over of each other. And you'll notice that they all have the same height. If I had a more complicated model, we would start seeing more peakedness and less peakedness out of some of the individual items. So here, the only thing we can really compare is the difference in central tendencies. And I can go with an item plot if I want to look at individual items. So here, I could either name the item, the column name, or I can specify which one, first, second, third, fourth. Here I specify the first one, which if I look up here is going to be, it's going to be VPMT1. They changed the order on this in the plotting, but it's VPMT1 is the first one in the data set. I can plot the trace. And so here it's giving us values. And we can look at the expected item score. And so this is individual item scores. You'll notice that here, this plot and the expected value are the same plot. So that's because it's a race model with zeros and ones. If we had nominal responses, this would look very different because it would be giving us probabilities of individual responses. Actually, there's two distributions being displayed here. There's the likelihood of 0 and the likelihood of 1. Well, they add up to 1, so I only need one present at a time. If I had multiple options, it would be a lot more interesting. So if I had 3, so think of it right now, pretend that there are 2 plots on here. One that goes down from left to right and one that goes up from left to right. And so the down is 1 minus the other one. Now, pretend that we have 3 options. So here in the example we have in front of us, it's a 0 or a 1. All right, so there's a probability of 0, probability 1. Now, pretend that we have 3 responses. There's a probability of 0, probability of 1, and probability of 2. Okay, so then there's 3 distributions, and we would see those 3 distributions on each of the plots here. Now, the expected value of the item scoring only makes sense if we have numeric values. Now, let's look at some other functions for MERT models. All right, so we can get the M2 model fit statistics. I misspelled statistics, but. And you'll notice that we have some values going up. We have a 95% confidence interval on the root mean squared error. We can compare nested models with log likelihood statistics. Now, you'll notice that I'm calling ANOVA, but it's not actually running ANOVA. Remember, I don't get any p-values. So I am comparing models, but I'm not getting ANOVA value back because we don't have necessary assumptions for there to be ANOVA. Remember, ANOVA comes from the F-test. The F-test has normality assumptions. We don't have those here. We can look at item fit statistics. So we can look at individually on the items in the whole orchestra of the model, which is a little bit complicated. We can look at the fit statistics. We can look at the summary of the model objects. Now, it's not very interesting because we use a Raish model. Since it's a Raish model, it's not that complicated. So these guys are all the same because of all the assumptions that are going into it. If I had a more complicated model structure, this would be much more interesting. And because I only have one latent variable going on, we only have one there. If I had more, this would be a more interesting aspect. We can also calculate bootstrap standard errors for estimated model. Now, something about this. So whenever I do bootstrap, bootstrap does a very good situation when we don't have sufficient assumptions. All right, so there are assumptions being assumed for us to get certain values fitted. Well, what if I don't have those assumptions? What if I'm working through and it looks like, no, that doesn't make sense. It's not reasonable for my situation. Well, bootstrapping is always a good choice for that. And so here we can see some output. If you run this code, the bootstrap will be the part that takes the longest by far. Now, we can also look at linear dependencies between items. And so I can go through and get get the values and the standardized values. And so you notice that they're different above and below the diagonal. One's for the values, one's for the standardized values. You'll notice that all the values below, or so all the values above the diagonal are less than 1 in magnitude. Well, here we have like 11 and 12, 12.9. And so that's because these are unstandardized. We can extract the raw coefficients. We can get the person fit statistics. Now, this will give us information on each and every individual. Now, I didn't want to have that print each and every individual, so I went ahead and put a head statement so that we only get the tops, just so that we can get a feel of what the results would look like. And we can also get factor estimates for each of the individuals in the study. And once again, this is going to give us a value for each observation. I didn't want us to get blasted in the face by numbers, so I just used the head function. All right, well, that's all I've got for you. Take care and goodbye.